Alright guys, welcome to Continuity Part 2. In this video we're actually going to look at specific examples of some functions and see why they are not continuous and maybe why they're continuous at certain points. So we're going to be applying those three rules that we talked about, the three conditions that you need to be a continuous function. So let's consider the function below. This is a piecewise function. Okay, so we have two pieces here. We have x plus 3 and my x values have to be less than or equal to 2. And then I have x squared where my x value has to be greater than 2. So here is the parabola where x is greater than 2 and I have an open circle, so I plugged in 2, I got 4. Okay, and here is my parabola, and x plus 3 where x is less than or equal to is this red graph right here. Now, this function is not continuous. Number one, if you can't draw the graph without lifting your pencil, it's not continuous. But we can't use that as a formal definition of why something's not continuous. We have to show it algebraically. So this function is not continuous because there's a jump at x equals 2. Okay, this has jump discontinuity. So we go from here at 2, 4, open circle, and we jump up here and finish the graph. Okay, so this is a jump discontinuity. The function is not continuous, but let's look at which conditions it fails. So if we note that the limit of f of x as we approach 2. So if we approach 2, we approach from the right, we get 4. If we approach the limit from the left, we get 5. The limit here does not exist. F of 2 is actually 5, because we have 2 would go into this function. F of 2 equals 5. The limit does not exist. Those two things do not equal. So this fails condition 2, and it also fails condition 3. It fails condition 2 because the limit at this point does not exist. Okay, and we also fail number 3 because f of 2 does not equal the limit as x approaches 2 of our function. Okay, in example 2, let's consider the function f of x equals 5 over x minus 2. Now, this function is discontinuous. This is called essential discontinuity, right? We can't simplify this quotient, and so we have a vertical asymptote at 2. Now, this is a discontinuous function because the denominator, I would say, can't be 0 or can be 0. So f of 2 does not exist. We can't eliminate that. So if we have 2 in for x, we get something that's undefined. This is an essential discontinuity. This would fail rule number 2. And it actually fails the first condition. F of 2 does not exist, and so that would fail condition 1. So this function is not continuous. Okay, in example 3, we don't actually have the graph. So let's see how we can do this and figure out where the discontinuity is. So I look at my function, and we're not taking limits here, so there is no limit. We're just looking at this function and saying, is this function continuous or not? This is a rational function, so it's probably going to be discontinuous. So first thing I try to do, I try to factor both the numerator and the denominator, which I can, into x minus 3 times the quantity x minus 5 over x minus 1 times the quantity x minus 5. So the x minus 5s can be removed. So what would happen here is that we would have x cannot equal 1 and x cannot equal 5. However, we've removed the 5, okay, because we have a simplified numerator and denominator. We have factors we can cancel out. So this is actually a removable discontinuity. There would be a hole. That hole would be at 5 comma 1/2. So I have my simplified function. If I plug this in, I get 2 over 4, which is 1/2. And so when x is 5, we get 1/2. So you have to be careful, even though 5 can't be in this domain, I still want to plug it in to see where the gap is. This is a removable discontinuity. We would say this would fail condition 2 because, it would fail condition 1 because f of 5 would not exist. Okay, so let's look at one more example. So in example 4, We've done another piecewise function. I have my quadratic, x cannot be 2, so that's pretty nice. So I have my blue parabola going through the origin, and I have a hole here at 2, 4, because even though x can't be 2, I'm going to plug that in and make it an open circle. This second part here, x equals 2 when you get 5, that's an ordered pair. Okay, that's the point 2, 5, which I've marked here in red. So this function is not continuous, number one, because I have that hole here where x is not defined on the parabola. So here's another thing we can look at, which conditions it fails. The limit as we approach 2 is 4. However, f of 2 is equal to 5. So the limit as I go from right to left of 2, I get 4. So the limit exists, it's 4. But that's not what f of 2 actually is. F of 2 is actually 5. This would fail rule 3. It does pass rules 1 and 2. However, the limit and the evaluation of f of 2 does not exist. Okay, so let's look at, I said one more example. We finally have one more example after this, an example 5. And this one is just actually showing you how we can tell if a function is continuous. Number one, if it's a polynomial function, it's going to be continuous. But this is a piecewise function. Not really easy to graph the quadratic, but I think we can just look and apply our 3 conditions to see if this is true. So we're looking to see if this function is continuous at a specific point, the point x equals 1. So 1 is the key point, it's our interest, so let's see. Does f of 1 exist? Meaning, can one of these two equations include 1? And the answer is yes. X in the second linear equation here, x is greater than or equal to 1, so I can plug 1 in and I get 9. So f of 1 exists. Does the limit exist as we approach that? Yes, we do. Or yes, it does. The limit happens to be from the right and left also equal to 9. And finally, does the limit of f of x approaching 1 equal f of 1? And that's true. We see that they're both 9, and that's true. So the condition 3 is met. So that is, I'm blanking here. That is continuity part 2. 5 examples of that. If you guys have any questions or comments, you can just type them below, or you can email me at nicholas.bennett@dc.gov. Thanks.